Today, we're diving into a fascinating study that brings together quantum physics, superconductivity, and magnetic levitation to measure one of the most elusive forces in nature, the Casimir force.
Yeah, it's really cool stuff. The Casimir force is this tiny, almost mysterious pressure that comes from quantum fluctuations in empty space between objects. It's like the vacuum itself is gently pushing or pulling things at the nanoscale.
Exactly. And even though it's incredibly weak, it actually plays a big role in how really small machines and devices behave. Plus, it's a window into fundamental physics, helping us test ideas about gravity and even dark matter.
But measuring it? That's the tricky part. The force is so faint that it's easily drowned out by vibrations, thermal noise, and just the challenge of keeping surfaces perfectly aligned at distances smaller than a micron.
Right, and most experiments use a sphere and a flat plate setup, but they often rely on something called the proximity force approximation, or PFA, which treats the sphere as a bunch of tiny flat plates. The problem is, this approximation tends to overestimate the force, sometimes by up to 2 orders of magnitude.
That's a huge difference. And on top of that, the real properties of materials and temperature effects make things even more complicated.
So enter magnetic levitation. Imagine a tiny magnet floating above a superconductor, suspended without any mechanical contact. It's like a magnetic cushion that isolates the system from vibrations and friction.
Yeah, that's a game changer. Because the sphere is levitated magnetically, it can oscillate freely, making it an ultra-sensitive force sensor. Recent advances in this field, levitodynamics, have pushed force sensitivity down to mind-boggling levels, like 10 to the minus 23 newtons per root hertz for spheres about 100 nanometers in size.
That's almost unimaginably small. The study we're discussing looks at a system where a tiny magnetic sphere made of nickel is coated with gold and levitated above a superconducting niobium plate cooled to around 7 Kelvin. That's about minus 266 degrees Celsius.
The gold coating is key because it doesn't respond to magnetic fields, so it isolates the magnetic effects from the Casimir force. Meanwhile, the niobium plate, being superconducting, exhibits the Meissner effect. It expels magnetic fields and creates a repulsive force that levitates the sphere.
So the sphere experiences 3 main forces: gravity pulling it down, magnetic repulsion pushing it up, and the Casimir force pulling it toward the plate.
And these forces balance out to create stable equilibrium points where the sphere can levitate at a fixed distance. What's neat is that the position of this equilibrium can be tuned by adjusting the external magnetic field.
Now, about the Casimir force calculations, this study goes beyond the usual PFA. Instead, they use a more exact scattering theory that accounts for the real geometry and material properties, giving a much more accurate picture.
They also include realistic models of gold's and niobium's electromagnetic properties at low temperatures. And importantly, they consider the finite penetration depth of magnetic fields into the superconductor. That affects the magnetic levitation force quite a bit.
Yeah, the penetration depth isn't 0, so the magnetic field doesn't just bounce off the superconductor perfectly. It actually penetrates a little, which changes the repulsive force.
So what did they find? The system shows stable equilibrium points at distances between about 700 nanometers and 2.5 micrometers from the plate.
And thermal fluctuations cause less than 2% uncertainty in the sphere's position near equilibrium. That means the system is very stable and precise.
The Casimir force itself ranges from several femtonewtons at submicron distances to smaller values at micron distances. To put that in perspective, a femtonewton is a millionth of a billionth of a newton, so incredibly tiny.
But the exciting part is that these force magnitudes are well within the detection capabilities of current or near-future magnetically levitated sensors.
Plus, the interplay of forces allows the sphere to oscillate like a tiny harmonic oscillator. Shifts in its oscillation frequency reveal the gradient of the Casimir force.
And these oscillators can have quality factors as high as 10 million, meaning they can oscillate for a very long time before damping out, allowing for extremely precise frequency measurements.
That's crucial, because the higher the quality factor, the better you can detect tiny shifts caused by the Casimir force.
Another interesting point is how the forces scale with the size of the sphere. The magnetic force scales roughly with the 6th power of the inner radius of the magnetic core, while gravity scales with the cube of the radius. The Casimir force scales differently depending on the distance, but generally less strongly.
So tweaking the sphere's size can control the magnetic levitation force quite a bit. But it's trickier to boost the Casimir force in the same way.
The study also discusses how the distance between the sphere and plate can be measured with interferometry, a technique that can detect position changes down to fractions of a nanometer.
That's impressive. And they note that vibrational noise and measurement noise are relatively small compared to thermal noise, which is expected to be the dominant source of uncertainty.
Looking ahead, this approach could revolutionize how we measure tiny quantum forces. It opens doors to testing new physics theories, including those related to dark matter.
And from a practical standpoint, it could help design better nanoscale devices by giving us a clearer understanding of how these quantum forces affect their behavior.
Future work might include accounting for electrostatic forces, surface roughness, and pushing measurements to even smaller distances, below 100 nanometers.
Plus, studying the role of superconductors in Casimir interactions, which has been tough so far, could become more accessible with this method.
So to sum up, this study combines quantum physics, superconductivity, and magnetic levitation to create a highly sensitive, stable platform for measuring the elusive Casimir force.
By carefully balancing magnetic repulsion, gravity, and quantum attraction, the system achieves stable levitation and precise force detection.
It's a great example of how pushing the boundaries of precision measurement can have wide-ranging impacts in both fundamental physics and nanotechnology.
Definitely. It's exciting to see how these advanced techniques come together to tackle such a subtle but important force.
Well, that wraps up our deep dive for today. Thanks for joining me in exploring this fascinating intersection of physics.
Thanks, Liam. Looking forward to our next conversation.